Okay, I'm going to remove this, and we'll go from current slide. Okay, now glad you're here. I wish the others were here as well. Sorry, I'm a little congested still, so hopefully we'll make it from here. Oh, here's my pen. Okay, still kind of hoping others would show up. Okay, we're in chapter 11, Vectors in the Geometry of Space. We're in section 11.5, Lines and Planes in Space, and we're on page 792, the lower part of the page. We had just done example 5. Oh, here comes Kyle. Good deal. Okay. So Kyle is here. Okay. So the top half of the alphabet, half of you are here. The bottom half, nobody's here. So hopefully the others will be coming in too. Any questions, concerns, problems, issues before we get started? Okay, I guess not. So as I was saying before, we're in chapter 11, Vectors in the Geometry of Space, in section 11.5, Lines and Planes in Space, and we had just done example 5 last Wednesday, middle of page 792, so now we're at the bottom of 792, and it's referring back to this theorem. I think I'll flick back to let you see the theorem, if it will flick, but it's not flicking very well now. Let's see. There it is. The distance between a plane and a point, Q, not in that plane, would be the distance, its projection of the point PQ. Now the point P is in the plane, point Q is not in the plane, so this is a line that's going from the plane up into space somewhere to point Q. Okay, you dot that with the normal to the plane, take the absolute value of that and divide it by the magnitude of that normal vector. Okay, the normal vector is made up of the direction numbers. Okay, and here comes James. Good deal. Hold on a minute. Let me get James in here. All right, now we got the bottom of the alphabet. We got a representative. So 3 out of 8. Glad y'all are here, but wish the others were here as well. Let me make sure there's no one else in the waiting room. Nope, just the 3 of you. That's all I see so far. Okay, and for some reason only one name is showing up on the screen at a time. Earlier this morning when I had my first class, all the names showed up, so I don't know why Zoom does what it does. Okay, but James, as we were talking, we're in chapter 11, Vectors in the Geometry of Space, section 11.5, Lines and Planes in Space, and we were making reference to this theorem 11.3, which gives you the difference between a point not on a plane and a plane, and they give you some point that is on the plane. So P is on the plane, Q is not on the plane, and you want the difference from the plane, the distance from the plane to that point Q not on the plane. And you do the dot product of P, Q, P being on the plane, Q not on the plane, with its normal vector, and then divide by the magnitude of the normal vector. Okay. And I can't get it to advance. Okay. Now, there we go. From that theorem, you can determine that the distance between the point Q, x0, y0, z0, and the plane, and remember the plane is named ax plus by plus cz plus d is equal to 0. Okay, That distance then would be the dot product between the normal vector for this plane, which would be the vector A, B, C. That's the direction numbers for your equation for the plane. Those give you the normal components, the components of the normal vector of that plane. Okay, so then it would be A times x0 minus x1. Now, they haven't said it here. The point P, remember, is on the plane, and that point would be x1, x2, x3. I'm sorry, x1, y1, z1. Okay? Now, I know this is a little backward from what we usually do, and why they're doing it this way, I'm not exactly sure, but the point from P to Q would then be, Q is the terminal point. Whoa, here comes Emmanuel. Let me get him in here, and I think we will have half the class here, and that's good to see. Now the bottom half of the alphabet has caught up with the top half, 2 people each, and half the class is here. So hopefully the other 2 will be coming in as well. All right. And for those who got here a little later, we just got back from Georgia, and the temperature changed significantly from what it was when we left and when we got back. And my hands are freezing right now. We haven't warmed up yet in the house. So if I sound like I'm a little hoarse, that's probably contributing to that as well. And Emmanuel, we're on in Chapter 11, Vectors in the Geometry of Space, Section 11.5, Lines and Planes in Space, and we're on the slide that the bottom part of page 792. And we were just talking about, from the theorem we just flicked back and saw, and you can go back and see it on YouTube video a little bit later, you can determine the distance between some point Q, x0, y0, z0, not on the plane, in the plane, and the plane ax plus by plus cz plus d is equal to 0, whereas your direction numbers are a, b, and c. Those values tell you the normal vector to that plane. Okay, the normal vector to the plane. Now what they didn't include here is the point P is on the plane, so the point PQ would be Q minus P, which is sort of backwards from how we usually do it. We usually do the larger number first and the smaller number second, but because this is PQ and P is x1, y1, z1, therefore these are a little backward seeming, but they're perfectly fine. And what's even more fine is the fact that it's an absolute value, so it doesn't really matter which order you do them, though it's usually you get. So the normal vector A, B, C, the vector PQ from P on the plane to Q not on the plane, that would be x0 minus x1, y0 minus y1, z0 minus z1. The dot product would then be A times x0 minus x1, B times y0 minus y1, C times c0 minus z1. Whatever that comes out to, that dot product, take the absolute value of that and then divide it by the magnitude of your normal vector, the square root of a squared plus b squared plus c squared. The d, you notice here, doesn't come into it at all. Okay, now here's another way to express what we just said. Okay, now this is not quite what we were looking for at all. Okay, if you think of this, that the let's see how to express this. the distance here, the little d here, right here, it's not a distance, but little d here, is subtract ax minus by minus cz. Subtract that from both sides. So that gives you that little d here is minus ax minus by minus cz. At point 1. Okay? Because this is on the plane. This point is on the plane. So therefore, that satisfies this equation. And all you have to do is plug in x1, y1, z1 there, subtract them. Okay? Now, that gives you the d here. Minus ax1 minus by1 minus c z1. That gives you that value there. Okay? I hope I said z1 at the end. I meant to. And so basically, what you've done is just written the absolute value of the product of your A times your Q values plus that D that you had there. Divide by this. Okay, so that's a rather interesting culmination of what these this formula will give you. Okay, now let me see, it won't advance. Let me click on the slide again. Okay, that formula for the distance between a point and a line in space resembles that for the distance between a point and a plane, except that you replace the dot product with the length of the cross product and the normal vector in with the direction vector for the line. Lots of substitution there. So here's theorem 1114, the distance between a point and a line in space. Okay, the distance between a point Q and a line in space is D is equal to P cross Q, P cross U, PQ cross U divided by the magnitude of U, where U is a direction vector for the line. Goodness, my hands are freezing. And P is the point on the line. Okay, so that's the distance between a point and a line in space, which we had, I thought, earlier. Yeah, well, they're giving it to us if necessary again. The point distance between a point and a line in space is the magnitude of the cross product of PQ, P being a point on the line, Q being a point in space, okay, not on the line. Cross that with the direction vector for the line, which is your ABC, okay, and where P is a point on the line, Q is a point not on the line, and that gives you that. So that's the distance is a cross product. Whereas the one for a PQ of P is on a plane, Q is not on the plane, cross that, dot that with the n divided by magnitude of n. That gives you the distance formula between a point and a plane, a line, a plane, the shortest distance between that. And this one is the distance between a point and a line in space. Okay. Oh my goodness. They don't do anything else with that. Oh, and I'm sorry, I skipped example 6. So let's go back and do example 6. I was so focused on, there was example 5. There was that statement. I skipped this skip to example 6 here. So let's go to the whiteboard. Sorry, my hands are just freezing. So let me get this box taskbar out of the way here and move the white space whiteboard as far left and up as I can get away with to give me maximum white space. I think that'll just about do it. Okay. Goodness. Taught my first class and I didn't even notice how cold it was, and I guess it's because I ate a salad and that was chilly, but anyway, now I'm freezing. Okay, here's example 6. I'm going to have to get my book in my lap in order to read it well. Okay, finding the distance between two parallel planes. Here's two parallel planes. The first of these is 3x minus y plus 2z minus 6 is equal to 0. The second of these is 6x. Oops, where in the world did that come from? Okay, this is aggravating. Okay. All right. 6x minus 2y plus 4z plus 4 is equal to 0. Now, the first thing I want to note here is, yuck, my wires are getting caught on everything possible, is these are parallel planes. How can you tell? Look at the direction numbers. 3 minus 1, 2. 6 minus 2, 4. Exact multiples. 2 times the first is the second. Now, how do you know they're not the same plane? Because that fourth value there is not twice. Twice negative 6 is not 4. Okay, it would be negative 12. So therefore we know these are parallel. They have the same normal vectors, but they're not intersecting. Okay, so that's the first thing to notice. They are parallel planes, which they said they were. They show you the picture in the book, which I'm not about to try to draw. I will show it to you on the slides in case you can see. Oh, I don't know. My camera, I can't tell where it is because they are not showing. I don't know why Zoom is not picking up the camera, but it's not. So I can't do that. Okay. Now, these are two parallel planes. They're shown in your book. If you got your book, you can see them. To find the distance between the planes, choose a point for the first plane. Well, let's just call this one the first plane. If I could get my, there it is, thing to show up. Okay? We need a point on that plane. Well, let's pick a point x, y, z that we know is going to make that true. 2, 0, 0. You see, if x equal 2, y is equal to 0, and c is equal to 0, then this would be 6 minus 0 plus 0 minus 6 equals 0. So there's a point that's on that plane. Excuse me. Okay. Certainly not the only point. Sorry. Oh, that sneeze must have brought in Jesus. So let me get him here. We are now more than half the class is here. That's good to see. So Jesus, yuck, is here. I just knocked my Wacom board onto the floor because I was trying to reach across there. And I don't know how in the world these wires can get so tangled. They were straight this morning and now they're tangled again. But anyway, all right, so this point is on this plane. And Jesus, we're on in chapter 11, vectors in the geometry of space, 11.5, lines and planes in space, and we're at example 6 at the top of page 793. They gave us these two planes, 3x minus y plus 2z minus 6 is equal to 0, and 6x minus 2y plus 4z plus 4 is equal to 0. We know they're parallel planes because the normal vectors for this one and that one are just multiples of each other. So the normal vector here would be 3 minus 1, 2. Normal vector here would be 6 minus 2, 4. Exactly. The second one is exactly twice the first, which means they're parallel to each other. If the normals are parallel, the planes have got to be, unless of course they're the same point. Are they the same plane? They're not, because this D is not also, this is a minus 6 here. If you multiplied that by 2, you would not get plus 4. So obviously they're not the same planes, but they're parallel. Okay. It says pick a point in the first plane. The easy one to do, one of the easy ones, you didn't have to do this, was 2, 0, 0. Because when you put a 2 in here, you get 6 minus 0 plus 0 minus 6 equals 0. Now, just as a verification of what we've done, 2, 0, 0 is not on this plane because that would be 12, 0, 0 plus 4 is not equal to 0. So obviously that point is not on the second plane, it is in the first plane. Okay, now, so now we have a point on the first plane, not on the second plane. We want the distance between the two planes. Okay, if you flick back, if you've got your book open to 1113, the distance between a point and a plane would be this. D is equal to, and it depends on which one you want to use now. In my mind, this last one that we just did, sorry, would be pretty easy to use. Okay, and that goes like this. Okay, now what you have to determine is which one you're going to use. Okay, and it really doesn't matter too much, except you have to make sure that your x0, y0, z0 is a point that's off the second plane. Okay, it cannot be on the it's on the first plane, not on the second plane. So this distance would be A. Okay, now we can use this point here, this plane here. So this will be A, which is 3. Well, I'll write it out for you. A x0 plus B y0 plus C z0 plus D, absolute value of that, divided by the square root of A squared plus B squared plus C squared. Okay, that to me is the easiest formula to use. So what do we use here? This is our A, B, C. Okay, here's our point x0, y0, z0. Okay, the point that's on this plane but not on, let's see, did I say it backwards? The point Q okay, I think we have to use this A, B, and C, okay, because this is the one that this point is not on that plane. Okay, so this is the A, B, and C that we're using, and the D that we're using too. The plane that's there and the point that's here. Okay, so let's do this one. The absolute value of 6 times 2, well, that's an absolute value sign, plus, and it doesn't really matter here because our y and z are both 0, plus 4 times 0, I'm sorry, that's a minus 2 times 0. Not that it matters any, because it's still 0. Okay, minus 2 times 0 plus 4 times 0, that's the C0 here, plus 4. Oh, and here's Houston. Let me get Houston in here, if I can get my fingers to thaw out. Goodness gracious. My hands are freezing. And they weren't in the first class, and you would have thought it would have only gotten warmer, but it hasn't. So Houston's here. So that makes us only missing Esther and Laron. So let me make sure they're not here somewhere in the waiting room. Goodness gracious, my hands are freezing. Oh, here's Houston again. He must have had to leave and come back, or he didn't get in fully the first time. Okay. Nope. 6 people, nobody else waiting. Okay. No, 7 people. Wait a minute. Oh, Houston's here twice. Okay. Don't know why, but Houston's here on 2 different ones. One of them the microphone's working, the other, no, both of them the microphone's working.
I've been trying to join since I have no idea. I've been here this whole time. It's just, I don't know what's going on.
Yeah, I don't either. My wife was saying earlier that it may be internet's going to get very unstable because everybody's probably twittering and tweeting and everything about the election coming up. So it could be that we could be losing the bucket pretty quickly. Hopefully not, but glad you're here now and that we can actually hear you. Okay, and that you can participate. And we just got home a couple hours ago, and the house was a little cool, but now my fingers are freezing, and I don't know why. Okay. Anyway, we're on in Chapter 11, Vectors in the Geometry of Space, 11.5 Lines and Planes in Space, and we're doing Example 6 at the top of page 793. They gave us these 2 parallel planes. Here's the first one, if I could get the pen to show up somewhere here. There it is. There's the first plane. Here's the second plane. Okay. How do we know they're parallel planes? Look at the direction numbers. 3, minus 1, 2, 6, minus 2, 4. Exact multiples of each other, meaning that the normal vectors are parallel to each other. Or that they're the same plane. Well, they're not the same plane, because if you did 2 times this, that would be 6 minus 2, 4. 2 times this would give you a minus 12. This is a 6 minus 2, 4 plus 4. Definitely not the same numbers, okay? But they're parallel planes. Now the distance, and we had just done this right before you came in, the distance between a point not on a plane and the plane. So the plane, the A numbers here, A, B, C, and D, this is the A, B, C, and D for the plane that this point here is not on that plane. Okay, how do we choose this point? You just pick any point that would make this statement true. So why not choose x equal positive 2? That would give you a plus 6, and then y is equal to 0, z is equal to 0. Those both contribute 0, minus x equals 0. Obviously that point is not on this plane because that would be a 12, 0, 0 plus 4. That's not equal to 0. Okay, so pick that, and then we're going to do, this is an absolute value sign. It looks like a 16. It's not a 16. That's absolute value. So pick the direction vector here, the direction numbers here, 6, -2, 4, and the D here, 4, and then multiply that by the point not on this plane, which is our 2, 0, 0. So it gives you 6 times 2 minus 2 times 0 plus 4 times 0 plus 4, and then divide that by this, which would be the square root of 36 plus 4 plus 16. A squared plus B squared plus C squared. Okay? Alright, now, what does that give you? My fingers are frozen. I don't know why. This would be a 12 plus 0 plus 0 plus 4. 12 plus 4, 16 over, absolute value, that would be 16. And this would be 40 plus 16 is 56, the square root of 56. Okay, well, that would be 16 over. Now, I know that 4 will go into 56 16 times, right? No, 14 times. 14 times 4 is 56. So this will be 2 times the square root of 14, right? I'm doing it in my head. So this would be 8 over root 14. Now, yeah. Goodness, my fingers are frozen. Okay. Let's see if I can make my phone work. They hurt. Okay. I don't have to turn it sideways to get my thing. 8 divided by the square root of 14, about 2.138 is what I got. They rounded it to 2.14. Good answer. Okay. Brr. All right. Now, that's where we ran into, and sorry that I got this a little screwed up this morning. My fingers are frozen. Okay, we're still on 11.5. That was the formula we just used, and we certainly came up with that result. And for some reason it's not resuming at the slideshow here. Okay. And this is the slide we were going to next. Goodness, my hands are cold. The formula for the distance between a point and a line in space resembles that for a distance between a point and a plane, except you replace the dot product, between a point and a plane with the cross product, which and the normal vector with the direction vector of a line. Okay, So the distance between a point and a line in space, we went over this before, but since Houston wasn't here, then we'll do it again. The point P that's not on the line and a line in space, the cross product between the point P, Q, P being on the line, Q being not on the line, and the direction vector for that line, which has the direction numbers as its components, where U is the direction vector of the line, P is a point on the line, Q is a point not on the line. This is the direction, the distance between those. Now, that's where the slideshow ends, but we've got one more example at least to do. Okay, so let's do example 7, which will take us back to the whiteboard. I'm so sorry, my feeling a little warmer, but goodness gracious, for some reason, like I said, this morning was no problem, but this afternoon it's just cold and my hands are icy. Now, here's example. Find example 7, bottom of page 793. Find the distance between the point, so here's the point Q, and the coordinates for that point are 3, -1, 4. And the line, I can't write, my fingers are so cold, and here's how we represent lines. X is equal to -2 plus 3t. Y is equal to -2t. And Z, I can't get my pen to write. This is such an aggravating board. Okay, Z is equal to 1 plus 4t. Hit it again. Okay. Okay, so find the distance between that point and that line. Okay. Okay, cynic that I am, I want to make sure that this point is not on that line. Okay? Now, I think the easiest way to do that would be to verify that, let me just see here before I get carried away here. If 3 is equal to -2 plus 3t, that would mean, let's just write that down, 3 equal -2 plus 3t. Add 2 to both sides, this will give you 5 is equal to 3t, so t would be 5/3. That would be your parameter. Well, if you put a 5/3 in here, y would be -10/3. Well, that y is not -10/3. So sure enough, that point here is not on that line. So that was just a verification. Okay, and now my eraser won't pick up, and I don't know why. That's so aggravating. This is what, the first time I've used the eraser and it's not erasing. I don't think I can pull up something down here. Okay, So basically, this is just garbage here. Sorry about that. I thought I would be clever and show you how you can verify it's not on the line. Okay. Now, the formula here says that the distance between a point Q and this line P, L or whatever you call it, whose direction vector is U. Okay, so let's identify a few things here. First, the point P that is on this line. Q is not on the line, P is. Well, what point would that be? That would be -2 for X, 0 for Y, and 1 for Z. Where do you get that? Just put simply 0 for T. That would be a -2, 0, 1. Okay, so this point is on the line, that point is not on the line. Okay, so what we want to do here, the distance between this point and that line would be the cross product of PQ, vector PQ, now this will be a magnitude of that, cross the normal vector for this line. Okay, well, no, the direction vector for this line, I think is how they say it. Yeah, the direction vector. Direction vector is what we call N. That's why I called it normal vector. It's not. Direction vector divided by the magnitude of the that direction vector. Okay. Well, we're going to need to set up your cross product. Okay. And the cross product would be I, J, K, I, that's supposed to be an I, J. And again, I don't think my eraser is going to show up. Okay. Now, sorry about the slant here. I don't know why it's picking up. Let's do the point between P and Q. That would be 3 minus a -2 would be 5. -1 minus 0 would be a -1. 4 minus 1 would be 3. And then repeat the first two, 5 minus 1. Okay? And then the last vector, the normal vector here, would just be our 3, -2, 4. Those are your direction numbers, 3, -2, 4. Then repeat 3, -2. All right, now your down diagonal here would be a -4i. Your down diagonal here would be a 9j. And here comes Esther. Good deal. Let me get Esther in here. Goodness gracious, this. Okay, I'm hanging on to my board this time. Okay, so Esther's here. We're only missing Laurent. Hopefully he'll be here soon. Okay, let me make sure he's not out there waiting somewhere. Nope, we've got 7 total with no Laurent. Okay, so Esther, we're in chapter 11, vectors in the geometry of space, 11.5 lines and planes in space, and we're doing example 7 at the bottom of page 793, finding the distance between a point and a line. Okay, they gave us a point, 3, -1, 4, and this line, x equal -2 plus 3t, y is equal to -2t, z is equal to 1 plus 4t. Okay, I first went through and just illustrated that this point is not on that line. And how I did that was plug in x equal 3 here, okay, into this equation here, and that gave us t is equal to minus 5/3. Okay, 5/3, I believe it was. Then I plugged in the t here, and you found out, nope, that's not. Now, the point P is on this line here. How do you get that? You just pick out these 3 points here, -2, 0, 1. That point is on that line. This point is not on the line. So how do you get the distance between this point not on the line and this line here? Well, the formula is the vector PQ, that's your initial minus, final minus initial, so it would be 3 minus -2, which is a 5, -1 minus 0, which is -1, and 4 minus 1, which is 3. And then the cross product of those two, whereas your n vector, your direction vector, are the components here, 3, -2, 4. So that's what you put down here, 3, -2, 4. Repeat the first two columns, I, J, for both of those. And that's what we're in the process of doing. All right, the first is -4i plus 9j, and then the last down diagonal here, if I can get my pen to show up in the right place, is minus 10k. Okay, minus 10k. Okay, now I'm not going to. My eraser is not working for some reason today, so we're going to ignore those and now do your up diagonals. Okay, now the up diagonals are always opposite, so this will be plus 3k, and this diagonal would be plus 6i, and the final up diagonal would be minus 20j, because you always do the opposite when you're going the up diagonal. Okay, well, what does that give you? The numerator is then going to be 2i minus 11j minus 7k. Okay, that's the cross product of those two, and we're going to take the magnitude of that over the magnitude of your normal vector, which was 3, -2, 4. Okay, so let me go on and write that one in. 3 squared is 9, plus -2 squared is 4, plus 4 squared is 16. Okay. I'm sorry. All right, so that numerator would be the square root of 4 plus 121, big number, plus 49, okay, divided by 29, square root of 29. Okay, now this would be 121 plus 49 is 170, plus 4 is 174, so that's the square root of 174 over the square root of 29. Now I don't know that off the top of my head, but let me see if I can get my calculator to work. My hands are so cold I can hardly move my fingers. Okay, so I'm going to have to turn it sideways to get the thing to come up. 170, whoops, not taking 174 square root of that divided by 29 square root of that equal something on the order of 32.5 0.31. That's a pretty big number, so I did something wrong with that. 2 minus 11 minus 7, that was right. I think it's my punching in the numbers because I punched them in. So let me try this again. 174. I think my square root sign did not work. Divided by 29 square root equal. Yeah, 2.45 approximately. And yeah, that's what they got, 2.45. Sorry, I don't know what I did wrong. I have fat fingers and a very tiny little buttons on my calculator, and sometimes they don't get along well at all. Like right now, those fat little fingers are cold as ice. Okay, that finishes 11.5. Okay, always the concept checks are good to look at, think through, make sure you understand. Okay, then homework exercises here would involve number 5. It should be at Calc Chat. Any of the odds 7 through 11, they should all be at Calc Chat. 9 should be at Calc View. 13 or 15 should both be at Calc Chat. 15 should be at Calc View. 17 to 23 should all be at Calc Chat. 25 to 27 should be at Calc Chat. 29 or 31 should be at Calc Chat. 33 or 35 should be at Calc Chat. 37 should be at Calc Chat. Any of the odds 39 to 43 should be at Calc Chat, with 39 being at Calc View. 45 to 55 should all be at Calc Chat. 47 should be at Calc View. 57 or 59 should be at Calc Chat. 61 or 63 should be at Calc Chat. 65 or 67 should be at Calc Chat, with 65 being at Calc View. 69 to 73 should be at Calc Chat. 75 to 81 or 81, sorry, 75 to 81 should be at Calc Chat. 79 should be at Calc View. 83 and 85 should be at Calc Chat. 87 and 89 should be at Calc Chat, with 87 at Calc View. 91 and 93 should be at Calc Chat, with 91 at Calc View. 95 and 97 should be at Calc Chat, with 95 at Calc View. 99 should be at Calc Chat. You can explore doing either 101, or 103. They should both be at Calc Chat. 105 to 111 should be at Calc Chat. 113 through 117 should be true false, and they should be at Calc Chat. There is another special project at the end of page 797, distances in space, and you can certainly look at those as well. Okay, now I'm sorry, we came back from Georgia this morning, leaving there, got up around 5 this morning in Georgia, which is 4 o'clock this time. I'm running kind of low on everything, so hold on just a minute. Let me get a little caffeine and sugar, see if I can boost some energy here. I'm still anemic. I feel like I'm better than I was last week, but still pretty low of energy, so periodically I have to boost it a little bit, or I feel like I do. All right, any questions on 11.5? Okay, we've just got 11.6 to go, and that, by the way, is going to be the last section in chapter 11 we're going to do, and this title is Surfaces in Space. Any questions before I leave the screen share and go to 11.6? And 11.6 is not showing up. This aggravates me no end. I brought up 11.6. It's here. There's 11.6 there. And I'm going to clear this out of the way, make sure I've got it here. Okay, let's see if I can pull it up now. There's 11.6. Okay. Now, hopefully you can see that so far. Let's go to the slideshow. If I could get the slideshow to show up. Why in the world the cursor won't show up? There it is. It won't, still not showing, but I made it indicate where it was. Okay. Hopefully you can see Chapter 11, Vectors in the Geometry of Space. 11.6 are surfaces in space. Now, by the way, this topic, you might say, is what back when I was in college, long time ago, they called this analytic geometry. And this was the very first section we did in Cal 1. Now it's one of the early sections they do in Cal 3. Of course, I had 5 quarters of calculus back then. They do 3 semesters of calculus now. Why there's such a disparity, I don't know. But here are our objectives. Recognize and write equations for cylindrical surfaces. That's one thing. Recognize and write equations for quadratic surfaces. That's another issue. That's basically what I'm calling analytic geometry. And then recognize and write equations for surfaces of revolution, which is not too far off from some other stuff we've been doing. So we'll start with cylindrical surfaces, then we'll do a little bit of pause, and I'll do a review of what we call conic sections, because that's where your quadratic surfaces basically are based on. Okay, so let's start with cylindrical surfaces. Now, if I say to you, what is a cylinder? I bet you most of you would picture in your head a tin can, right? A right circular cylinder. Now, I don't have a tin can here. I have a Dr. Pepper bottle, but the portion right there between here and here is basically what we usually think of as a right circular cylinder. And that would be true. But that has really nothing to do, well, a little bit to do with what a cylindrical surface is, but cylindrical surfaces do not need to be right, nor do they need to be circular. Just be cylindrical. Well, what do we mean by that? It says you have already studied 2 special types of surfaces. One of these is a sphere. A sphere is x minus x0 squared plus y minus y0 squared plus z minus z0 squared is equal to r squared. Now that's one way to express it. I'm going to express it a way I like to a little bit better, and this is based on what we're going to do in the future. Okay? Let's divide everything by r squared. Where r is the radius of that sphere. So this would give you x minus x0 squared over, well, you can't read the 2 there, over r squared plus y minus y0 squared over r squared plus z minus z0 squared over r squared is equal to 1. Now you'll see a little bit later why I prefer writing it this way. Now here's the thing to note for a sphere. The center of the sphere is this point x0, y0, z0. That's the center of the sphere. Okay? Other things to note. The denominators are all the same numbers, r squared. Okay? And this is a 1 there, so that's where you divided r squared by r squared. Okay? Now, the other thing, every one of these is a plus sign. That's a plus sign, that's a plus sign, that's a plus sign. So anytime that all 3 of your denominators are the same, and your numerator, if you have a difference there, the variable always is first, x minus, y minus, or z minus, then the numbers, x0, y0, z0, those come second. The x0, y0, z0 is the center of the sphere, and the r is the radius of the sphere. Okay, now the second special type of surfaces is the one we were just talking about earlier today and last time. Ax plus by plus z0 plus d is equal to 0. I hope I said that right. Ax plus by plus z0, cz plus d is equal to 0. That's a plane. Okay, spheres have that square in them, everywhere a square, so that's going to be a curved straight structure. This is, everything is linear, first power, that's going to be a planar structure. A third type of surface in space is called a cylindrical surface, or simply a cylinder. But do not think this is a tin can. Okay, a cylinder is a much broader definition. The first one they show you looks like a tin can, so don't get it too confused. To define a cylinder, consider the familiar right circular cylinder. This is a very special case of a cylinder. What makes it right circular? Well, number one, the circular part means the base, the line, the curve that you have here defining this cylinder is a circle. That's why they call it a right circular cylinder. Okay? Now, where does the term right come from? Well, this cylinder has an axis that's parallel to one of your coordinate axes. This one happens to be the z-axis here. Okay, in fact, that is the center of that, and so therefore the plane that's formed, that circle that you formed there, is perpendicular to that axis. Okay, this happens to be the z-axis. Now, the cylinder is generated by a vertical line that moves along that circle. X squared plus y squared equal a squared. Okay, now this is a circle in the xy plane, no z component at all, and this then would be the right circular cylinder centered at the z-axis. Okay, that would be it. So you draw your figure in the xy plane, and then imagine a line that's perpendicular to that plane and moving around that circle that you just did, and that forms a cylinder. Now notice a couple of things about that. There's no top and no bottom. Okay, that line extends forever, up and down. Okay, that's a right circular plane, right circular cylinder. It's not a tin can, because a tin can is finite on top and bottom. So that's where this does deviate a little there, but that's be a right circular cylinder. Why? Because this equation for it, x squared plus y squared is equal to a squared, that would be the equation of a circle in the xy plane. Now again, I would rewrite that as dividing everything by a squared, and that would be x squared over a squared plus y squared over a squared is equal to 1. Okay, that's sort of like I like to see them represent these basic equations, where a is the radius of that circle in the xy plane and centered at the origin, which means the z-axis. Okay, that's a right circular cylinder. But guess what? A cylindrical surface is any curve in one of your planes, and then you draw a line along that curve. Okay, that circle is called the generating curve for the cylinder, as indicated in the following equation. Here's a definition of a cylinder. Let capital C be a curve, any old curve in a plane. any plane, any curve in the plane, let L be a line not in a parallel plane. So in other words, this line cannot be, okay, I know I can't see where I'm waving my hands here, but I'll try to get you an idea. Okay, let's say here's a plane, a plane where C is located, and C can be any curve that's in that plane. L is a line not in a parallel plane, so it wouldn't do any good for L to be down here. That wouldn't make any sense. L is any line not in a parallel plane, so therefore L is going to cross that plane where C is located in some place. Now that L does not have to be perpendicular. It can be at any angle whatsoever except parallel. Okay, so it's like that. And the set of all the lines parallel to L intersecting C is called the cylinder. Okay, so it doesn't have to be perpendicular. That would be a right cylinder. It doesn't have to be a circle. That would be a right circular cylinder. This would be any the set of all the lines parallel to the L intersecting that cylinder, that curve C. The curve C is a generating curve, also called a directress. Okay, now we're going to see that term occasionally, not going to use it a lot, but it is a very common term in analytic geometry. Directress of the cylinder. The parallel lines are the rulings, which is an interesting kind of curve there, a point there. Those are the rulings that follow that curve. Now remember, that curve could be a sinusoidal curve, it could be just a parabolic curve, it could be any kind of curve, just a random curve. And then any line not parallel to the plane that you're talking about, that line, that curve is on, any line that's not parallel to that follows the track of that curve, that forms the cylinder. Okay, and the C is called the generating curve or directress of the cylinder, and all those parallel lines are called your rulings, which is sort of an interesting terminology too. Now, without loss of generality, you can assume that C lies in one of the three coordinate planes. That's fine. There's no problem there. Okay, it makes things a little easier. Moreover, the text restricts our discussion to right cylinders, so it doesn't. The angle between the line and the plane has to be a right angle. Okay, so we're going to restrict ourselves to right cylinders, not right circular cylinders, but right cylinders. So cylinders whose rulings are perpendicular to the coordinate plane containing that curve C. Okay, now here is the XZ plane here. Okay, the XZ plane. There's the x-axis, there's the z-axis, and you have your rulings that are parallel to that XZ plane. Okay, now the curve is in the XZ plane. You can draw that right along the XZ plane there, but your rulings go infinitely parallel to the y-axis in both directions, parallel to the y-axis, infinite number of steps there. Now that is a curve. Doesn't say what kind of curve it is, just some type of a curve there. Okay, and we're going to take the curve in one of your goodness, I'm cold, coordinate planes, the XZ plane in this case, and that puts the rulings parallel to the y-axis. Okay, and there's your cylinder. Not a closed cylinder, definitely not a closed cylinder. A right cylinder for sure, but not a closed curve. So it's not a closed cylinder. All right, that's a cylindrical surface. For a right circular cylinder, shown back in 1156, the equation of the generating curve was just that x squared plus y squared is equal to a squared. There, the plane, the generating plane, you might say, was the xy axis. The generating curve C was, I'm so sorry, I am so out of energy. Excuse me just a moment. The more I'm talking, the worse my throat hurts too. So I don't know if that's doing any good for my throat at all. It feels good, but it may not be doing any good. Now, the xy plane is your plane where the generating curve is. The curve is this circle, x squared plus y squared equals a squared. Or x squared over a squared plus y squared over a squared is equal to 1. Now, to find the equation of the cylinder, note that you can generate any one of the rulings by fixing the x values of the x and y and then allowing z to take on all real numbers. Okay? In other words, in this one, the z's go up and down as high and low as you want them to. Okay? All real values. In that sense, the value of z is arbitrary, therefore not included in the equation, because z takes on any value in the world. Okay, x and y have to be restricted to that circle in the plane, the xy plane. In other words, the equation for the cylinder is simply the equation of the generating curve. X squared plus y squared equals to a squared. Okay, and that's a cylinder in space. It looks like it's a circle in the xy axis. It's not. It's every line that traces that circle in the xy parallel to the z-axis. So the equations of cylinder, the equation of a cylinder whose rulings are parallel to one of the coordinate axes, contains only the variables corresponding to the other two axes, which are the ones that identify your generating curve. All right, so here it says sketch the surface represented by each equation. The first of these is z is equal to y squared. Well, obviously the x-axis is not involved with this at all, so if you are drawing the I'm going to draw the try to draw the z-axis. Yuck, that gets worse and worse and worse. There's the z-axis, there's the y-axis, here's the x-axis. Okay, I'm going to see if I can clean up that z-axis a little bit there. Okay, let me try it one more time. Something like that. That's your z, this is your y, and there's your x. I say x and write z. Okay, now z is equal to y squared. Okay, now if you choose a plus or a minus y here, okay, that's supposed to make my negatives of those. Let's let y be, say, 1, okay, or minus 1. Z is going to be 1. So basically in the YZ plane we have a parabola. Ugh, that's a pretty ugly looking parabola, isn't it? And your values of x are going to be parallel to the x-axis but going infinitely in both directions. There's your shape. Okay, it's a parabolic cylinder. Okay, and my picture stinks. Okay, it's really, really awful, but that's what it looks like. Okay, it's a parabola in the YZ plane and the traces are parallel to the x-axis. Okay, now let's see if theirs look a little bit better than mine. Okay, the first curve is a cylinder whose generating curve is a parabola in the YZ plane, and that's what it looks like. Okay, now they have theirs oriented slightly differently, but that's what it looks like. Now, it's so hard to to look at this sometimes and get it right. Okay, there is your parabola in the YZ plane. Okay, like this. Okay, opening upward in the YZ plane, going through the origin in the YZ plane, and then your scales or scalings, the markings there are these things parallel to the x-axis. Okay, there's one they've shown there. You could show a whole passel of them in both directions, and that would be your cylinder. Okay, parabolic cylinder. Okay, now the second one of these, okay, is z is equal to sine x. Okay, now if I do the same type of thing I did before and make our z-axis here, the y-axis here, and the x-axis here, here we're in the xz plane. Okay, I'm going to extend the negative here, a negative here, and the negative here. Okay, so in the xz axis we have z is equal to sine x. So when x is equal to 0, z is equal to 0. When x is pi halves, z has gone up to 1 here. When it's 0, it's 0 again. When it's down here, it becomes, it's so hard to draw these. This is your the sinusoidal curve in the, and that really stinks. Okay, now your traces, you might say, are then parallel to the y-axis, and the y-axis actually is 1, but then you got one parallel here, 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 here. All these are parallel to that y-axis, wherever that is there. So that's a really lousy drawing here. So hard to draw three-dimensional on a two-dimensional shape. Okay. No, and I was only supposed to go from 0 to 2 pi. So sorry about that. It should have started, and I did in the wrong direction too. I should have started coming up here and going down. Okay, sorry about that. 0 to 2 pi. Forget about the part down here, and these would be the shapes this way. Going up here, 0 there, back up here. And then those would be the shapes. Sorry, I was thinking that was the C part there. Okay. And there's your sinusoidal curve. Starting at 0 here, going up to +1, down to 0, up to minus, down to -1 and up to 0 again. Stopping right there. So it's one wave, one function of this. Parallel to the y-axis, period. In fact, the y-axis is one of the traces. Okay. And then at x equal pi here, you have another trace. I can't get my pen to show up. Where is the pen? Oh, I'm off the, well, there it is. Okay, so here would be another trace parallel to y-axis. There's one, there's one, there's one, there's one. Okay, so you have all those traces that cut parallel to the y-axis, that cut through that one shape from 0 to pi halves of that sinusoidal curve. Okay, so there was the rest of example 1. All right, now before we get to quadric surfaces, how are we doing time-wise? We got a little bit of time. I want to point out to you a few shapes, okay? All right, we've already hit a couple of them, okay? One shape is a parabola, and parabola basically looks like, and we saw one earlier, I believe it was z is equal to y squared or something like that. This would be a parabola along in the YZ plane. Okay, you could also have a parabola in the XZ plane, which would be the one we're used to as x squared is equal to y, or you could have a z is equal to x squared, and you could just fix any kind of a value here. One variable is to the first power, the second variable to the second power, which is the one I haven't done yet. X is equal to z squared. There's another one. Okay, so these are all parabolas. Okay, now hang on to that concept. Another shape that we have certainly is our circle. Okay, and a circle is, like I said before, x squared. Now, I was debating whether I should give you this in another form as well. I probably will later, but hang off of that. Okay, a circle would be x squared plus y squared is equal to r squared. We saw that in cylinders. Or three-dimensionally, x squared plus y squared plus z squared is equal to r squared, and x. All right, let's divide everything here by r squared. Okay, and you have something like x squared over r squared plus y squared over z squared over r squared plus z squared over r squared is equal to 1. Now that is a sphere. We saw that earlier. We're not going to go back and retrace that, but that's the sphere. Okay, now I think I will, well, okay, let's do, that's the sphere. Let's do what we call a ellipse. An ellipse is a lot like a circle, okay, except it's not. Okay, now a circle is x squared plus y squared plus z squared, or x squared plus y squared is equal to r squared, or any other two coordinates there. Plus sign in between, and if a circle, you can divide, all your denominators would be the same. Okay. All right, this thing is aggravating. Now, let me just, I don't draw them well, but that would be approximately a circle, right? Three-dimensionally, it would be spherical. Okay. An ellipse, on the other hand, is like that. An elongated circle. Now, it may be elongated like this or at any angle. Okay. Here's the key. Okay. You have x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. Okay, now here's the difference. Your A, B, and C, see, for a circle or a sphere, all these are the same. For an ellipse, two of them may be the same or all three different. It doesn't matter. That's what gives you the elongated shape there. Okay, now some of those, it won't be, and that's why this form is a little bit neater of a form, because if you can set everything equal to 1, then these give it away. So what are the keys for an ellipse? The keys for an ellipse are the signs are all positive, okay, but all three variables are raised to the second power, but your denominators are not necessarily the same. Now certainly if they are the same, a sphere is a special form of a circle is a special form of an ellipse, okay? And ellipses are special forms of circles, but not all circles are ellipses. Yeah, all circles are ellipses, but not all ellipses are circles. Okay, now, the next of these, and by the way, your parabolas, one variable is to the first power, the other variable is to the second power. Circles and ellipses, all variables are to the second power. All the signs are positive. Okay, so let's get to a third type, and I think I'm going to clear the screen because this is getting so murky. I got to get my pen to show up. There it is. Well, I don't know what I just did. Yuck, this is so aggravating. I don't know where the pen is now. Here we go. I don't know where my, look at that. It's just doing all sorts of weird things. Okay. I don't know how to get this back. Let me hit escape and see if that, yeah, there we go. All right, now let's see if I can find the pen again. There it is. All right. The third shape is one that looks like this. That shape is called a hyperbola. Okay, what makes a hyperbola is the fact you can have an x squared over a squared, a y squared over b squared, a z squared over c squared, and this can equal a 1. Now what did I leave off? I left off my signs. Let's just say the x is a positive and say this is a negative and that's a positive. Okay, that would be a hyperbola. Or this is going to be a negative and that should be a positive. That would be hyperbola. Okay, so here's a difference, and that's why I like to equal 1. Okay, those are your characteristics of hyperbola. These are not closed circles or closed shapes like a circle, a parabola. No, well, a parabola isn't closed either, or an ellipse. These have the possibility of a minus there, which would not allow them to close. Okay, now with those in mind, let's look at our quadric surface. The fourth basic type of surface in space is called the quadric surface. Quadric surfaces are three-dimensional analogs of your conic sections, and that's what I was just trying to give you, your conic sections. Circles, ellipses, parabolas, hyperbolas. Okay, and these are three-dimensional analogs of those conic surfaces. Okay, the equation of a quadratic surface in space, I'm trying to draw it with my finger on the wrong pad. A quadratic surface in space is a second degree equation. Maximum exponent there is 2, second degree equation, in 3 variables. So it's a spatial figure, 3 variables, maximum exponent is a 2. The general form, now we're not going to go to this general form very often, but the general form for an equation of any quadratic surface would be this: ax squared plus by squared plus cz squared plus dxy plus exz plus fyz plus gx plus hy plus iz plus j is equal to 0. Wow. We're not going to go with this, okay? This is the most general form, okay? There are 6 basic types of these quadratic surfaces. I mentioned the first, the ellipsoid. On the ellipsoid, the A, the B, and the C are all positives, okay? A special case of this would be a sphere, which the A, B, and C would all be the same length as well, okay? Now, the hyperboloid, which comes from a hyperbola of 1 sheet, and the hyperboloid of 2 sheets. Now, I don't know why they jumped into naming these before they showed them to you, but they should have shown them to you first, I think. But we'll get to those in a minute. The elliptic cone, okay? There's an ellipsoid, this is an elliptic cone. And we'll point out the difference between those, quite a bit of difference. Then we have an elliptic paraboloid, and a hyperbolic paraboloid. So it's going to be helpful to remember. An ellipse is a closed surface with A, B, and C all positive. Okay? Hyperboloid of 1 sheet and 2 sheets, at least one of those is going to be negative and the other 2 positive, or 2 positive and the other 2 negative, other 1 negative, or something like that. Okay? An elliptic cone, that's a very special case. We'll come to that in a minute. And then elliptic paraboloid. Now that's going to be a special case. And then a hyperbolic paraboloid is a very special case. So let's look at each of those. The intersection of a surface with a plane is called the trace of the surface in that plane. To visualize a surface in space, it's helpful to determine its traces in some well-chosen planes. Okay. The traces of quadratic surfaces are the conics, which are your circles, ellipses, parabolas, and hyperbolas. Okay? Those are your traces. Those traces, together with the standard form of the equation of each quadratic surface, shown in the following table. And again, I wish, well, I guess, yeah, they do show you the picture. Okay. The first here is called an ellipsoid. Remember, an ellipse is it's like an elongated circle. That's exactly what it's like, an elongated circle. Now, I don't like this rendition of it particularly at all. Okay? It's okay. Those are all correct, but there is a better way to describe it. Okay? Now, this one I like a little bit better. It doesn't quite show everything, but it does show, well, it shows pretty much everything. Okay? Though it could be improved a little bit. Now, I'm sorry, I'm freezing to death again. I don't know what's going on here. Alternating between being okay and my hands just freezing. And the temperature is not changing that much. It cannot be changing that much. So, hold on just a minute. I guess it's the anemia. I don't know. I'll blame everything on the anemia now. Okay. Now, Remember, an ellipse is a closed figure that's sort of an elongated circle. Okay? Now, let's take this picture right here. If I can get the pen to show up here. There it is. Okay. Now, in the XY plane, if you draw this elongated circle here, you see the blue line back there, that's the ellipse in the XY plane. In the XZ plane, that's the ellipse. Okay? It almost looks circular there. It may be close to it. Okay? And in the YZ plane, there is your ellipse. Very definitely an elongated circle there. Okay. Now, how I think this would have been improved if they had done, rather than doing, like you might say, meridia here, if they had just shown all these are ellipses too. Okay, that's not a very good one there. And here would be ellipses this way and this way, every way you cut it. Now these here, parallel to the YZ plane, those are very nicely ellipses going up and down. They did not show the ellipses going up and down the XZ plane or the YZ plane. Okay, I wish they had. Here they just showed the ones in the coordinate axes. Okay, here is your general form, just like I described before: x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. Notice everything squared, the x, y, and z. That gives you closed curves everywhere, and the signs being positive between every one of them. Okay, now if you were to say, let z be 0, say, that would be the xy ellipse down here. Okay, or y is equal to 0, that would be the xz ellipse here. Okay, or whatever you've got left. Let's see, what would that be? The x equals 0, that would be the YZ ellipse there. Goodness, I'm freezing. So there's the ellipsoid. Always a closed shape. Every dimension you would have an ellipse. However you cut it, everything parallel to any of the planes would be an ellipse. Now, why they jumped to the hyperboloid of one sheet, I'm not really sure. But it's an okay thing to do next. Notice the difference here. You get x squared over a squared, y squared over b squared, z squared over c squared equal 1. Looks very similar to this. The difference is one of these, and only one of them, has a minus sign. The other two, and this is a plus. Okay, so everything's a plus except for 1. What you notice about that 1, the one that's a negative here, that's your axis. Okay, that is your axis. Okay, now that kind of makes sense. In the fact that since this is a minus here, right here, if you had x equals 0, y is equal to 0, z anything other than 0, it never can happen, okay? Because you would have a negative here equal a positive there. It cannot happen. So therefore, the z, that is your axis, and there's actually no place where that z can be, where your x and y can both simultaneously 0, basically. Now, here are other things to note here. All right, let's focus a little bit on the a and the b here. If these are two different numbers, then what you have are ellipses here, right? Ellipses here and here. All these traces here parallel to the XY plane are ellipses. Okay? Now, where does it get the name hyperboloid? Well, remember, that shape here that are opening opposite ways on opposite sides are called hyperboloids. Hyperbolas, okay? And every one of these traces would then be a hyperbola. The traces parallel to the XY plane, those would be ellipses, but perpendicular to XY plane, whether it's YZ or XZ, those would be hyperbolas. Okay. Now, that's with the one ratio that's a negative, that's going to be your axis. So that's hyperboloid of one sheet. Now, next we're going to go to a hyperboloid of two sheets. Notice what's happened there. You have a separation between the sheets. And what's the difference here? You have two minuses. In this case, the one that's the plus, that's your axis. The two that are minuses, those are then the ones here. Now, here's a difference here. If Z were equal to 0, which is down here, notice that you'd have a negative minus a negative plus a negative equal a positive. Not going to happen. Okay, so a hyperboloid of two sheets is not going to ever have the two that are negative. If the Z cannot be, the one that's positive can never be 0. Okay, because then you'd have a negative plus a negative equal to a positive. Not going to happen. Okay. Now, again, you're parallel to the XY axis. These form your ellipses. Okay. Now, how you do that, your A's and your B's, of course, the Z cannot be 0, and in fact, goodness, my throat's hurting like crazy. The traces that are parallel to the XY plane, which are defined here, okay, the Z's have to be greater than the XY sums here, okay. You can't have any Z's in between those 2 points there, because this allows you to have, okay, here's another way to look at it. In the XY planes parallel to that, you have basically something that looks like a ellipse, because x squared over a squared plus y squared over b squared. In this case, it would be z squared over c squared minus 1. Okay? As long as z squared over c squared is greater than 1, you would have these ellipses going in space like that. Now, let's go back and look at the traces here. And this is what I was trying to show here. Every trace that you have parallel to the XY, YZ, and XZ planes, all of those are ellipses. In a hyperboloid of one sheet, there are ellipses parallel to the XY plane, whichever your axis is here, okay, but everything else are hyperbola. Okay. In hyperboloid of two sheets, also your ellipse is parallel to the XY plane. It's just some values that it can't happen, okay, but then the others are ellipses here and hyperbola otherwise. A hyperbola in I don't know why that popped up. Okay. But you have hyperbola in 2 dimensions, 2 of your traces, ellipse in 1 trace. The difference being the traces here are that way and this way and this way and that way, whereas in 1 sheet the hyperbolas are that way and this way. Alright, now let's go to the next case. Okay, hyperboloid of 1 sheet, you have an ellipse there in the center. Hyperboloid of 2 sheets, you have no ellipse in the center. An elliptic cone, you have a 1 point and 1 point only in the center. You don't have a ellipse here. You have ellipses above and below, just like you have ellipses above and below here, but everything coalesces around the origin. Okay. Hold on just a minute. I am about to lose it. I'm about to lose my pen too. Okay. I'm so sorry. I've been up since, like I was saying before, I think 5 o'clock Eastern Time, which is 4 o'clock Central Time, and I got, well, maybe less than 6 hours sleep, so I'm fading fast. Okay, now again, let's see, I didn't point this out. Yeah, here in our hyperboloid of 1 sheet, everything parallel to the XY plane, or whatever your perpendicular to your axis there, which is the one that is the one and only minus sign there, that's your axis. These are ellipses along here. Every trace along there is an ellipse, which we saw here too. These are ellipses here all along there. But the traces in the XZ plane and in the YZ plane, those are all hyperbolas. Okay, and that's what they show here. Now in the hyperboloid of 2 sheets, it's the axis is the one and only positive. So in 1 sheet, the one and only negative, that's your axis. In the hyperboloid of 2 sheets, the one and only positive is your axis. And above and below that gap that you have there, these are ellipses again here, but then they're hyperbolas in this direction here or in that direction there. Okay, so those are all hyperbolas. Okay, now let's do the elliptic cone. Elliptic because, okay, let's take a look at the formula first. 1 and only 1 negative, that's going to be your axis. Okay, the Z again. A lot like the hyperboloid of 1 sheet. Your 1 and only 1 negative here is going to be your axis. The elliptic cone, the 1 and only 1 negative there, is going to be your axis. What's the difference though? Here it's equal to 0. Everything else before now has been equal to 1. This is 0. What does that mean for you? The only way that the X, Y, and Z could be 0 is if that's equal to 0. So that point 0, 0, 0 is on that curve. Notice that is not on your ellipsoid, it's not on your hyperboloid of one sheet, nor is it on the hyperboloid of 2 0. 0, 0, 0 can't exist in any of those other forms. It can exist here. Okay? So not too much of a surprise that it looks sort of like this hyperboloid of one sheet, except now the girdle has been tightened so that you're at one point right here. Now, again, the traces parallel to the XY plane, perpendicular to the axis here. These are all ellipses. Every one of them has been so far an ellipse. Okay? These are they say here these are hyperbolas parallel to the YZ plane and the XZ plane. They don't show that very well here. In fact, they show it really, really, really poorly. Because those don't look at all like hyperboles to me. Okay? These look like straight lines. Okay? That doesn't look like a hyperbola. Okay? And I don't see why they're saying they are. Okay? It says here the traces in the coordinate axes are parallel to the x-axis or intersecting lines. So that's where the straight lines are. That's correct. I guess what they're saying is the trace out here would be hyperbola and like this. They just don't show them well in any of the illustrations here. Not at all well. And back on this side, that would be, if you had a trace that way, that would be hyperbola as well. Not a very good drawing, not a good illustration of that at all. The difference is elliptic cone equals 0. The other three have all equaled 1. All right. Now, elliptic paraboloid, in fact, both of your paraboloids, there's not a 0 or a 1. You have a single variable here. Z to the first power is equal to some combination of x and y's to the second power. Well, that, remember, was what your paraboloid was. Z is equal to x squared, or Z is equal to y squared. Okay? Or y is equal to x squared, or x equal y squared. I mean, any one that, okay. So your axis is the thing to the first power here, okay, for an elliptic paraboloid. Why is it elliptic? Because your traces parallel to the xy plane here are all ellipses. Okay. Your traces in the xz plane are parabolas, and in the yz plane are parabolas. Okay. All of those are parabolas. Okay. That's why it's called a paraboloid. Now, if you have, and by the way, these two are pluses, and the pluses indicate ellipses. Okay. When you have the Z over here, that's going to be your, in a sense, it's kind of like the axis. Okay. In a sense. Okay. But here you have a minus sign there between these two. Okay. Now notice one of these is your y squared, one of them's your x squared. The x squareds, because it's negative, they have to be opening downward when you're okay. If you have what they call the saddle point, okay, here, those are opening downward. Hyperboloids, okay, hyperbola. I'm sorry, parabolas. Here's where the hyperbolic part comes in. The elliptic, the trace parallel to the XY plane here, those are ellipses. Parallel to the XZ planes here. Now this is not quite so obvious here. Okay, if you're going down this way, you have hyperbolas. Okay, if you're going this way, let's see if that's right. Yeah, you have a hyperbola in one, okay, and where that hyperbola is parallel to the XY axis here, okay, that's your hyperbola that's here and here, parallel to the XY axis. That's the one that you have hyperbola here. Set z equal to 0 or z equal to any number, and you have hyperbola there. Okay, now paraboloid, because you have a parabola this way or this way. Okay, now the one with the minus sign is opening downward when you have z is equal to y squared. That is, goodness gracious, this ear sets are bugging my head. But you have your parabola opening upward in the XZ plane here, opening downward in the, in the YZ plane here, because those are both positive here, opening downward in the XZ plane there, and sure enough, those are opening downward like this. Every one of these is a parabola opening this way in the XZ plane. In the YZ plane, they're opening upward. Every one of those is a parabola opening upward because it has a positive A, so you're opening upward like that. Okay, elliptic paraboloid, because these traces here are parabolic, the traces parallel to the XY axis are elliptic. Here the parallel to the XY axis are excuse me, goodness, my throat's hurting like crazy, are your hyperbolas. When you do these parallel to the XY plane, it just really doesn't show them well at all here, but these are, well, this one shows it best. This curves out this way, this curves back that way, so those are hyperboloids in the XY plane. That's this plane here, and they're parabolas on either of the other two, this way or this way. Okay, and I think that's beat them to death. Okay, how are we doing time-wise? We were supposed to have stopped about 15-20 minutes ago. Sorry about that, folks. We'll start next time with example 2 here on this slide. I've got my next class starting in just a few minutes. Sorry we went over. I'll see 3 of you in just a little bit. Any questions? Okay, let me